Hey, thanks. And I'd like to thank the organizers for inviting me to talk. I'm sorry I couldn't be there. I had planned to, but it just didn't work out. So as I think that was Venki, wasn't it? As Venki said, I'm going to talk about orderable groups. So in this talk, gamma is always going to be an arithmetic group, or to be more like the previous talk, gamma is a lattice and a semi-simple Lie group. It's the same thing for my purposes. But at the very start, you could take gamma to be any countable group. But later on, I definitely want to think about just arithmetic groups or lattices, however you want to say it. And the questions I'm going to talk about is just whether there exists a left invariant total order on the group gamma. And let's call that order lambda. Let me explain what that means. First of all, to say it's a total order means that for all x and y, either x is less than y, or x is greater than y, or x is equal to y. So it's not a partial order. For every x and y, they're comparable. And then left invariant just means that if x is less than y, then it's invariant under multiplication on the left. So ax is also going to be less than ay for all x, y, and a. So a group that has such an order is called left-orderable. So the same question is just whether is gamma left-orderable? That's the question I want to talk about. You've got an arithmetic group. I've got an arithmetic group, and I want to know whether it's left-orderable. And the most simple example is just the infinite cyclic group Z. Z is left-orderable. Although, yeah. And in fact, the left invariant total order is just the usual less than relation. That's a total order. And obviously, if x is less than y and you shift, x will still be less than y. Okay, but let's look at why people talk about this. This is one of the basic topics in algebra, or at least in group theory. So one of the motivations, or I'll talk about a few motivations for why people study this. The point is that if gamma is left-orderable, then it has some good properties. And the first one thing is that often people who study groups are interested in their actions. So you want to know what are the actions of gamma on some particular space, or even just does there exist an action on some particular space? And left-orderable means that there is an action of gamma on the real line R. Well, of course, there's an action. There's always the trivial action, but we want it to be non-trivial. In fact, let's make it faithful. So if gamma is left-orderable, then it in fact has a faithful action on the real line. And it uses the topology of the real line, so it's continuous. It's an action by homeomorphisms. And this is not really important, but also I want to say it's orientation preserving. So an action, any homeomorph to the real line is either orientation preserving or orientation reversing. Either it fixes infinity and minus infinity, or it interchanges them. Anyhow, so a left-orderable group always has an action on R, and in fact, that's if and only if. That's exactly what it means to be left-orderable. If you want to know whether a gamma has an action on R, that's the same as asking whether gamma is left-orderable. Another more algebraic motivation is that gamma being left-orderable tells us about the group ring. The group ring, the integer group ring of gamma, if gamma is left-orderable, it's easy to see that it has no zero divisors. And it's a famous old conjecture that this is true for all torsion-free groups. The torsion-free groups, the group rings of torsion-free groups never have zero divisors. And so some of the people who study that problem want to prove the conjecture is still open. It's not known in general. So one way to prove it for some class of groups is to show that the groups in that class are left-orderable. And in fact, that is the reason why many people study this. It's not my motivation. But another thing about group rings is that if gamma is left-orderable and the group ring of gamma is isomorphic to the group ring of some other group, then in fact, they're the same groups. This is not true in general, but it's a fact about orderable groups, that the group ring determines the group. And the last one is topological rather than algebraic. Let's say that gamma is left-orderable and it happens to be the fundamental group of some manifold, which I'll call M. Well, M has a universal cover, so there's a projection from the universal cover down to M. There's a covering map. And so, yeah, M tilde maps down to M. But the point is, if M if gamma is left-orderable, if the fundamental group of M is left-orderable, then the picture is like this. You can draw the fundamental group, you can draw the universal cover directly on top of M. And what I mean by that is you can actually embed the universal cover in M cross the real line. So each point of M, you just draw a line above it. You can put the entire universal cover in there so that the diagram commutes. Okay, that's motivation, but to me, it's just an interesting question. I guess I'm interested in action, so it's the first one that motivated me to look at this. But for whatever reason, the question I want to talk about is whether I have an arithmetic group and I want to know whether it's left-orderable. So yeah, one example. Let's let gamma be a free group. Now, this is an arithmetic group because it's essentially just SL2Z up to finite index is just SL2Z, and it's also the integer points also of SL1, 2, of course, up to finite index. So there's a little dot over the equal signs to indicate finite index. Well, in a free group, every subgroup, actually, and I'm not worried about every subgroup, actually, I just need the finitely generated subgroups. It's true for every subgroup. So in particular, every finitely generated subgroup has infinite abelianization. It maps onto the infinite cyclic group Z. A group with this property that every finitely generated subgroup maps onto Z is called locally indicable. And it's not difficult to show. It's been known for decades that any locally indicable group is left-orderable. If you have a locally indicable group, you can put an order relation on it that's invariant under translation. And I won't prove this in detail, but let me just give the idea. It's not difficult, but there's technicalities involved. The point is just that if you have an X and a Y, we need to decide whether X is bigger than Y or X is less than Y. And the way to do that is just choose some homomorphism. I mean, our group's locally indicable, so every finitely generated subgroup, such as the subgroup generated by X and Y, has a homomorphism onto Z. We use that homomorphism to decide who's bigger. Just compare X to Y by comparing phi of X with phi of Y. If phi of X is less than phi of Y, then X is less than Y. The problem is that you can't just choose these randomly. You have to be systematic about how you choose these homomorphisms. So for example, in order to make this homomorphism, this order relation transitive, that means if we have three elements, we assume, and this is done just by using Zorn's lemma, you pick these homomorphisms and make them compatible by using Zorn's lemma. We have to assume that the homomorphism for X and Y is just the restriction. I mean, it's a homomorphism, the subgroup generated by X and Y. It's a restriction of the subgroup of the homomorphism you defined for the three generated subgroup X, Y, and Z. Except that's the basic idea, is just that you choose these compatibly so that as you choose more and more elements, your homomorphism's consistent, except that won't always be the case. That's true unless X and Y are in the kernel of that homomorphism. If X and Y are in the kernel, then Z is just way bigger than X and Y. So transitivity holds without any trouble. Okay, all right, so that's background. SL2Z. Up to finite index, if you pass the finite index, it's left-orderable. That's been known for a long time, actually almost not as long, but still a long time. I proved long ago that if you look not at SL2Z, the next obvious thing to check is SL3Z. Well, take a finite index subgroup. No matter what finite index subgroup you take, it will not be left-orderable. So SL2 is left-orderable, SL3 is not. And by comparing these two examples and other examples, a conjecture was made for general arithmetic groups. If you have an arithmetic group that's left-orderable, then G has to be like SL2. It's got to be rank 1, and more specifically, the real rank has to be 1. Sorry. Yeah. Okay. So what that means is that if you look at the real points of G, it will have to be, the real points of G are very limited. It's either SO1N or SU1N or SP1N or F4. So of all the many semi-simple Lie groups, a lattice will not be left orderable unless your Lie group happens to be one of these four. And one thing I guess I'm assuming here that G is almost Q simple. So I'm going to look at irreducible lattices. And one thing to notice is that these last two groups, SP1N and F4, all their arithmetic subgroups have Kazhdan's property T. And it's a famous open question in the field of orderable groups, whether there exists an orderable group, a left orderable group, that has Kazhdan's property T. So my feeling definitely is that at least the lattices in SP1 and F4 are not orderable, but it would certainly raise a lot of eyebrows. If you could find a left orderable lattice of one of those two groups, that would be great, or prove that no Kazhdan groups are left orderable. Both of those are very good questions, and I have no idea how to solve them. Okay, so what I'm talking about today, I'm talking not specifically, I said at the start that I'm talking about left orderable groups, but actually what I want to talk about is this conjecture that left orderable subgroups have to have left orderable arithmetic groups have real rank 1. This conjecture, it's 30 years old, something like that. Just recently it was proved. The conjecture is true. It was proved by Bertrand de Rennes and Sebastian Hurtado. The preprint's been on the archives for a few years, but as far as I know, it still isn't published. But yeah, the conjecture has been proved. I had been trying to prove this conjecture, or just special case the conjecture, by using algebraic methods, multiply the Raghunathan technique of multiplying together unipotent elements, take centralizers, take normalizers, all that stuff. I never got very far. So very little was known, and but these two proved the conjecture in complete generality by using not algebraic methods. They used analysis. They used group actions and real analysis. And part of the real analysis, or a connection between the group actions and real analysis, is that they use harmonic functions throughout the paper. And so that's the main thing I want to talk about. I'm not going to talk about the whole proof, certainly not in any detail, but let me just talk about one ingredient, which is how harmonic functions, so some basic facts about harmonic functions, which are used in the proof. And first of all, let me just tell you what a harmonic function is. So let's assume, we've got this group, we've got an arithmetic subgroup gamma of G, but it doesn't really matter. We've got some group G. Let's assume some Lie group G. Let's assume that mu is a Borel measure on G. And also that it's a probability measure. So the total mass is 1. So the way to think about this, usually you just take like Lebesgue measure on a ball. That's the kind of thing that mu is. Mu is not the Haar measure in all of G. It's some compactly supported small measure. And then phi is some real valued function on G. We say that phi is harmonic, and technically harmonic depends on which measure you pick. So we should say that it's harmonic with respect to mu if, well, the mean value property for ordinary harmonic functions is that a harmonic function is equal, the value of a harmonic function at a point is equal to the average of the values on the ball around the point. That's the definition Furstenberg gave in general. We say that phi is harmonic if at every point, the value at that point is equal to the average of the values on the ball, on some ball, or whatever mu is giving us. If mu is the Haar measure on a ball, the big measure on a ball, then we're just averaging out for ball. But anyhow, it's a harmonic function is one whose values are the value at any point is equal to the average of the values at nearby points. Oops, sorry, no, I said the wrong thing. Yeah, this isn't saying anything. This, of course, phi of x is equal to average of phi of x, but it's true even if you translate. So if you translate around, instead of taking just the value phi of x, take nearby values and average them, you get the value at the point x. And that's got to be true everywhere if the function is harmonic. That's the definition. Okay, so I want to talk a little bit about a basic property of harmonic functions. So gamma, I'll take to be an arithmetic subgroup of some simple algebraic group, which I'll call G. Now so that's boldface G. Let's let ordinary G be the real point. So this is a semi-simple Lie group. Gamma is a lattice in this semi-simple Lie group. And for the purpose of this talk, it's fine if you just want to think of G as being SL3R. The theorem is new, the Hurtado theorem is new even for SL3R. It was known, the theorem was known in almost no cases. And to make life simpler, I'm also going to assume that G mod gamma is compact. So I'm assuming that G, the algebraic group, is Q anisotropic. We're doing analysis, and analysis is much easier on compact spaces. So yeah, so G is Q anisotropic. And remember, to say that phi is hard, I'm just recalling the definition of harmonic here. Now, it's a crucial theorem that's used in the paper and is very interesting, I think. We've got gamma is a subgroup of G. The theorem is that every harmonic function on gamma extends uniquely to a harmonic function on G. That's the idea. A harmonic function on gamma extends to a harmonic function on G, but this isn't stated quite right, because in order to talk about harmonic functions, it has to be harmonic with respect to a measure. Oops, yeah, I'll say, yeah, so it's not just that it extends uniquely, but harmonic, in order to state this, we have to pick some measure on gamma, which we'll call mu gamma, and some measure on G, which we'll call mu G. And that's the theorem, that every harmonic function on gamma extends uniquely to a harmonic function on G. So our function on the subgroup extends uniquely to the function on the whole group. And there is a technical issue here, though. So to avoid them, let me just talk about bounded harmonic functions. It's certainly true that any bounded harmonic function will extend. And in fact, I'm going to give a proof that doesn't need this, but in the situation I've described at the top of the page here, we have to be careful here. So let's assume our function is bounded. And, what are these measures? Yeah, mu gamma and mu G. They're not arbitrary. The theorem, let's just say the theorem is that there exists. You can pick a measure on G and a corresponding measure on gamma for which this is true. So that the harmonic functions on gamma can extend to be harmonic on G. And one of the main things I want to do today is just talk about the idea of the proof of this theorem. It's an ingredient in the Duane-Hurtado theorem, but it's the main thing I'm going to talk about today, is just why is it that harmonic functions in a subgroup extend to harmonic functions on the whole group. But to simplify the proof, to state this more easily, let me replace the real numbers with p-adic numbers. That makes the proof much easier. So the situation I'm in is that G is not the real points of my algebraic group, but the p-adic points. And so just think of it as being SL3 of QP, and gamma is some co-compact lattice in G. So if you want to think about in terms of arithmetic groups, what this means is that gamma is not actually arithmetic, it's going to be S arithmetic. And our set is, of course, the infinite place plus one finite, the finite prime P. So we've taken S arithmetic subgroups of arithmetic subgroups. The point is just that, let me just say what we've got here. So G is SL3QP. Gamma is a discrete subgroup. It's a co-compact discrete subgroup. I want to prove that harmonic functions on gamma extend uniquely to harmonic functions on G. To do this, let's let K be SL3 of the p-adic integers instead of the whole set of p-adic numbers. So that's a subgroup of G. And of course, I picked this because it's a very nice subgroup. It's a compact open subgroup of G. And now, I just said K is open. So G mod K, if you mod out K, the points are open, so that means that G mod K is discrete. And now let's look at, so this is G mod K. Let's also mod out by gamma on the other side. Well, G mod K is discrete, so the quotient's discrete, but G mod gamma is compact, so any quotient is going to be compact. So this space here, it's both compact and discrete. It's got to be finite. And a finite set's easy to work with, but to make it even easier, there's just finite many points. Let me assume there's only one point. Let me assume that this finite set is actually a single point. And what that means is that all of G is just K times gamma. everything in G is an element of K times an element of gamma. That's not quite right because I should have this finite set of coset representatives or double coset representatives, but let me not worry about that. Let me just assume there's only one coset representative. And then if you think about this means, that means also every element of G is K times gamma. And in fact, this intersection is trivial, it turns out, because gamma is left-orderable. Oh, I guess I was assuming, let's assume the intersection is trivial. Well, then topologically, G is just going to be K cross gamma. It's a Cartesian product. I can identify every element of G with just an ordered pair, an element of K and an ornament of gamma, because the map from K cross gamma to G, but by just multiplying, is going to be a bijection. All right, so this was the setup, and now I'm going to start proving that harmonic functions extend. And the first thing, though, is we have to pick our measure mu G, and it turns out it's enough just pick any by K invariant measure. So what that by K invariant means, if you take the measure of a set, it's the same as the measure of any translate. If you multiply by K, some element of K on the left, you get the same measure, or if you multiply on the right. And it's easy to find such a measure. They're easy to construct. So just choose, it turns out, if you take if you take your measure to be by K invariant, we'll be able to extend harmonic functions. Now here's the thing though, the key thing to notice is that if phi is harmonic for this by K invariant function, and remember, here's what that means. It means this phi is equal to the averages. Well, just look at phi of K times X. So that means I should put a K right here, but our measure is invariant under translation by K. So I can just do a change of variables, so replace G times K by G. So it turns out that that will not change the value of this integral. So it doesn't change the value of the function. In other words, if you have a harmonic function, it's got to be invariant under translation on the left. It's K invariant on the left. And from that, it's obvious that any extension is unique. If we have two extensions, if phi and psi are two different extensions of some function on gamma, and they're harmonic, so if you got two harmonic functions that both extend the same function on gamma, then they have to be the same. There's only, the extension is unique. And the way to see this is just calculate phi of some G. This is a warm-up for what I'm going to do next. So every element of G is just an element of K times an element of gamma. So I can take, instead of writing phi of G, that's the same as taking phi of some K times some gamma. But since phi is harmonic, it's got to be invariant under K, so that K just disappears. But we're assuming that phi and psi are the same on elements of gamma. So that's the same as psi of gamma. And now I just do the argument backwards. Psi is invariant under left, is K invariant on the left. And K gamma is just what I would meant by G. All right, so that was a trivial argument. The uniqueness is trivial. What we need to prove is existence. And we're assuming, recall, that G is K times gamma. And the measure mu, we're assuming, is by K invariant. Well, by Fubini's theorem, G is a product space. So that means we can write the integral mu G. Sorry, we can write the measure mu G. We can break it up as a product. It's a bunch of measures on gamma integrated across K. But the by K invariance is telling us that, in fact, we take the same measure on every slice. So in fact, mu is just a product measure. Since it's by K invariant, it's got to be just a product of a measure on K and a measure on gamma. And that makes it easy to prove, easy to construct the extension. If we have a harmonic function, if we have a function on gamma, it's easy to make an extension to G, to extend this to a function on G, just by defining, let's make it K invariant on the left. Any element of G is a K and a gamma, let's just ignore the element of K. Just define it to be whatever phi does to gamma. The exercise is to show that if phi is harmonic, so if we have a harmonic function on gamma, then the extension will be harmonic on G. And I'm leaving this an exercise, but let me give the idea. Let me sketch the proof here, and you can think about the details. So I'm trying to show that phi hat is harmonic. That means I want to show that exactly means that I want to show this integral is equal to phi hat of x. And I'm not bothering to write down mu sub g. Any integral with respect to g is respect to the measure on g. All right, so the thing is that this is what I want. But remember, the measure on g is a product. That means I can I can take this integral and turn it into a double integral. I can integrate over k and gamma separately if I let little g be k times gamma. So this is Fubini's theorem. It's telling us that I write the integral as a double integral. And now though, phi, so what am I saying here? Oh, yeah, the definition. Oh, I said something stupid here. Yeah, I should have said, all right, I should have said already. Yeah, so I was doing this a different way, but I made a mistake in what I wrote. So I should say that let's assume, and I'll say that this will show up in a minute, but I thought I didn't need it yet. Let's assume that x is an element of gamma. Yeah, so I should have done that. I should have said that x is an element of gamma. Then gamma times x is also an element of gamma. So I have k times an element of gamma. The definition of phi is that if you take phi hat of k times an element of gamma, it's just phi of gamma. So phi hat, this k doesn't do anything. We could get rid of that. When you take phi hat of k times an element of gamma, that's just phi hat of the gamma. Right? And so here we've got, and now this integral has no k's in it. So there's no reason to integrate over k. Just get rid of the integral. We're just integrating over gamma. And as I said, I should have taken right from the start x to be an element of gamma to make this argument right. But now if we look at what we have here, we're integrating phi hat of some gamma, some element of gamma, but phi hat of an element of gamma is just phi of gamma. Phi of the element of gamma. And now I'm averaging phi over gamma. Well, since phi is harmonic, that's just going to be phi of x. And phi of an element of gamma is the same as phi hat of that element of gamma. Just look, if k is trivial, you're just getting phi hat of gamma equals phi of gamma. So this is the proof when x is in gamma. I don't think I left out anything, but anyhow, this is certainly the idea of the proof when x is in gamma. And then to prove it in general, just use the fact that both the left side and the right side are going to be invariant under k. K invariance then gives you for all elements of G instead of elements of gamma. All right, so maybe I botched that up, but anyhow, it didn't do anything difficult. This was in the case of a p-adic group. The real case is definitely more complicated because you don't have if you look at G mod K mod gamma, if you mod out by K on one side and gamma on the other side, you don't get a single point, you get a whole manifold. So you have to argue, you have to work somehow with that manifold. And it turns out that what you do is you just take a random walk on the manifold to decide what your value should be. You don't have a single point, you take a random walk to figure out what values you should use. But anyhow, let me just assume we've got this theorem. And with that in mind, with that in hand, if we have the fact that harmonic functions on gamma extend to all of G, let me then give just the vague idea, some idea of how the theorem is proved.
Sorry, can I ask one question? So
Sure.
far you didn't use the higher rank assumption, right?
Absolutely not. Absolutely not. This is a very general theorem. Yes.
Thank you.
Yeah. Good point. Yeah. In fact, that was a very general theorem. We'll see higher rank come up in a little bit. Well, in a few minutes. Yeah, the question was, did I use the fact that I'm assuming G has higher rank yet? And the answer is no, but we will soon. Okay, so the theorem, remember what I'm proving the conjecture, which is that if an arithmetic subgroup is left-orderable, then the real rank has to be 1. And so actually, sorry, yeah, the real rank has to be 1. So as was indicated in the question, so actually what I'm going to do, in order to prove this theorem, obviously, we're assuming that gamma is left-orderable. And I didn't write it down here, but I'm going to assume that the rank is bigger than 1 and get a contradiction. That's the way the proof goes. So suppose the group of gamma is left-orderable, but G has higher rank. Let's see that that can't be true. Okay, well, gamma is left-orderable. And when I tried to prove these theorems, I used the fact that gamma is left-orderable. I worked algebraically, but the proof that actually works is not algebraic, it's analytic. It uses group actions, and it uses harmonic functions, and it uses dynamics. So instead of thinking of just as order, we use the fact that a left-orderable group always acts on the real line. And well, one way to try to approach this is, yeah, let's, as usual, let G be the semi-simple group that gamma is a lattice in. It's easy to see that G does not act on the real line, at least not non-trivially. And the reason is just that if you look at the stabilizer of a point, well, we're in a one-dimensional space, so the orbit is one-dimensional. So that means the stabilizer has to be a subgroup that's codimension 1. And that's a contradiction. A higher rank, in fact, SL2R is the only simple Lie group that has a subgroup of codimension 1. So in order to get a contradiction, one way to try to prove this theorem, and the truth, I did try to prove it this way, you could try to show that the action of gamma will extend to an action of G. That would give a contradiction immediately. Unfortunately, nobody has figured out how to make that argument work. So the actual proof is more complicated, but it's the same idea. The point is that we have to bring G into the picture. My proofs that didn't work, that only did special cases, worked with gamma. Working inside using the algebraic structure of gamma, you can do some special cases, but the proof that works in general requires using G. And so let's explain how we get G into the picture. That's the main point here. So we're assuming gamma is left-orderable, so it acts on R. It'd be great if we could extend the action to an action of G, but that's not what we extend. We extend something else. Or at least we don't extend that action. So it turns out a key to get started in this proof that works is to compactify the action. We've got an action of gamma on R. R is not a compact space, obviously. So it's been known for some time that you can construct a compact set containing R. Well, that's easy. Like there's the 1-point compactification. You could add 1 point in infinity, but that's not what works here. Instead, we construct a compact set, call it C, that has an action of gamma. So gamma is acting on R. I'm going to put R inside a bigger space that gamma acts on. But actually, C doesn't just contain that original copy of R. C is a union of many, uncountably many copies of R. In fact, it's foliated. So C is a foliated space with copies of R passing all through it. And each one of those leaves, each one of those copies of R is invariant under gamma. So instead of just having gamma act on one copy of R, we have it act on uncountably many copies of R, but we wind those all together into a compact set that gamma acts on that whole set, preserving each leaf. And the other thing is that we need this action to be non-trivial. In fact, let's say that the action of gamma has no fixed points at all. It's highly non-trivial. No point is fixed by the gamma action. That's the starting point of the Duane-Hurtado proof, is instead of trying to just look at the action of gamma on R, let it act on this bigger space that had been constructed by Duane and his co-authors in previous years. Okay, well, actually, we saw basically in the last talk that if you have an action on a compact space, if you have an action on a compact space, there will always be a stationary measure. And that was defined in the last talk, but let me give the way I think of a stationary measure for the purpose of this talk. So let's suppose we have a stationary measure mu, functional analysis, so it's explained in the last talk. To say that a measure is stationary, and we're talking about it's stationary for the action of gamma, what that means is if you take the map for each element of gamma, Well, pick some subset of C, let me call it A. Look at the measure not just of A, but of the translates of A. For each gamma, look at the measure of the set A translated by gamma. That's a function on gamma. To say that the measure is stationary exactly means that this function is harmonic. So it turns out, as was explained by Sahik in the last talk, by function analysis, he just took he took weak star compact, took a weak limit and stuff. You can always find a stationary measure. That means we have lots and lots of harmonic functions. Every subset, every measurable subset of C is going to give us a harmonic function. Well, okay, that's one thing. So we have this action. There's two things I want to do with this. First of all, put a stationary measure on that space. The second thing is to bring G into the picture. G probably doesn't act on C, but we can construct an action of G just by inducing this gamma action to an action of G. This is very classical. And in fact, it's the same thing that was done yesterday morning. There were, what were they called? Yeah, yesterday morning, the first talk yesterday morning used parabolic induction of representations. This is the same thing for group actions. Yesterday, we had a representation of a subgroup. From that, you got a representation of the whole group. Inducing an action is the same thing. If you have an action of a subgroup, you can make an action of the whole group, but it's not on the same space. You can't make G act on this tiny little space that gamma acts on. We have to make the space bigger. So what this does is this classical construction of constructing an induced action will embed C in some larger compact set, C hat, such that G will act on C hat. And, well, now, so gamma is acting on C. We knew that already, but now, since G is acting on C hat and gamma is a subset, a subgroup, it will also act on C hat. So we have an action of gamma on C, and we have an action of gamma on C hat. Well, the key condition here is that when we extended and made C hat bigger, we didn't change the gamma action that we already had. Gamma was acting on C. It'll still be acting on C in the same way. We construct all of G as acting on this larger space, but we didn't change what gamma did. We just made the space bigger so that other elements of G could act as well. C is still doing what it did do. And now I want to put these two together. I've got a stationary measure, so I have lots of harmonic functions on C, and I've got this action of G on a bigger thing. Well, we know that harmonic functions on gamma will extend to being harmonic functions on G. Well, we've got lots of harmonic functions on gamma. Every one of those will extend to a harmonic function on G. And by using that, it's not obvious, it's not trivial, but by using these extensions, we can actually then extend the stationary measure on C. It gives us harmonic functions. Those will extend to be on all of G. We can use those functions on G to actually make a stationary measure for the G action. So we find from the stationary measure on C, by extending, we can make actually a stationary measure for G. So we have a measure on the whole space C hat. Okay, so let me say, so this whole page here, the key thing that we did here was we had an action of gamma on R. We extended that, we made the space bigger so that we had an action of gamma on some set C. We now made C bigger to C hat so that G will act on it. And that has a stationary measure, which means that these translations, yeah, if you look at what you get by translating, the measures vary as a harmonic function. That's the situation we have. Okay, so all that, none of that was difficult. Definitely didn't give details, but nothing was difficult. The hard part, this is the key to the proof of the conjecture. The hard part is to show that this harmonic function, so for every set A, we get a harmonic function. The hard part, what Dewan and Hurtado have to prove is that, in fact, that harmonic function is constant. Or in other words, the measure mu, we're assuming it's stationary, but in fact, it's invariant. If you take the measure of any translate is the same as the measure of the original set. That's exactly saying that all of these uncountably many harmonic functions, every one of them is actually constant. And I'm not going to have time to explain how that works. Yeah, let me not try to do that, unfortunately. Maybe I can say a little bit. But here, in fact, yeah, maybe I'll have it. We'll see if I've got any time left. This is a place where we use the fact that the real rank is bigger than 1. In order to prove that this measure is invariant, yeah, I hope I can say at least a little bit. Yeah, I'll rush through a little bit where we see where real rank comes in. Okay, so we now know that this measure, it was constructed to be stationary, but the crucial thing, as Sahik said in the last talk, is that invariant measures are very rare. Stationary measures are everywhere. So proving that a stationary measure is invariant is very unusual, but they were able to do that. The stationary measure is actually invariant. So by restricting, I mean, mu hat's a measure on c hat, but by restricting down, we can get a measure on c. Now, this isn't obvious because c actually has measure 0, but there's lots of copies of c. But yeah, you can restrict down to get a measure on c. And since mu hat was G invariant, the restricted measure will be gamma invariant. This is not difficult. It's a straightforward restriction process. But now remember that C contains a bunch of copies of R, and gamma is acting on all these leaves. It turns out that then on each leaf, or actually on almost every leaf, there's going to be an invariant measure. And each leaf is a copy of R. So we've got an action of gamma on R that has an invariant measure. And from here, it's trivial. If gamma acts on R and preserves the Lebesgue measure, say it's preserving some measure, might as well be Lebesgue measure, it's acting by translations. For every gamma, there's some C, which depends on gamma. It's just a real number. So that gamma of X has to be just X plus C. The only homeomorphisms that preserve Lebesgue measure, that's the same as preserving distance, are just translations. Well, yeah, the orientation of preserving homomorphisms. Well, then this map C, since this function here, gamma is, we have a group action, the only way that C, that translating by various amounts can give an action is if C is actually a homomorphism. But this implies that, in fact, well, there are no homomorphisms from gamma to R. So C of gamma has to just be 0 everywhere. And here is also a place where we assume the real rank is bigger than 1, but this is very mild. This is not a very deep use. Well, I guess, well, no, it's a basic fact that in higher rank, there are no homomorphisms to R. Well, this is a contradiction. If you look here, if C is 0, that means the gamma of X equals X. Well, so that means the gamma action has a fixed point. But we assumed at the start there were no fixed points. Or actually, if C of gamma equals 0, then in fact gamma of X equals X for all X's. So the action wouldn't just have fixed points, it'd be completely trivial. So there's definitely a contradiction here. And I think I still have, what, more than 5 minutes, don't I?
I have 5 minutes or more.
Yeah, okay. So yeah, let me go ahead. I'm not gonna be able to do this very well, but let me go ahead and explain just again, well, the proof I gave so far was definitely just a sketch. Let me just give a very, very basic idea of how this thing is proved and we'll see that real rank comes in, even though I won't really give a proof here. So let me explain how to prove the hard part. Well, no, let me give just the most basic idea of how this hard part is proved. We're trying to prove that this measure is G invariant. That's the crux of the entire argument. And the way to do that is just G is SL3R or SL3QP, it doesn't matter. Let's let P be a minimal parabolic subgroup, so it's the upper triangulars. And let A be, as usual, the diagonal matrices. It's a split Cartan subgroup. It's definitely contained in P. And now, if you have an element of A, I want to define what's called the expanding horospherical subgroup. It's the elements of G that when you conjugate by A to the n, it gets bigger and bigger. Well, I said here that this tends to 1. That's because I'm letting n go to minus infinity. So if when you conjugate, if it goes to the identities, meaning gets smaller and smaller, then goes to minus infinity, that means these things are getting huge as you go to plus infinity. So that's why I put plus here. This is the expanding subgroup. It's the elements of G that are expanded as you go to infinity, which means they're contracted as n goes to minus infinity. Okay, so that's just notation. And we need a theorem of Furstenberg from 50 years ago that whenever you have an invariant measure, sorry, not invariant, that measure, whenever you have a harmonic measure, every harmonic measure for G comes from a p-invariant measure. Yeah, comes from an invariant measure for P. And more precisely, a stationary measure is always an integral of translates of a p-invariant measure. So any stationary measure can be written as an integral over G, sorry, an integral over K of the K translates of P, of the measure for P. And in fact, that measure mu P is unique, but we don't need that fact. But invariant stationary measures come from p-invariant measures. And now the key to the proof, yeah, so the hard part, in order to prove the hard part, what they show is that if this expanding if you've got some element of A such that the expanding horospherical subgroup is contained in P, and there's some technical condition I don't want to talk about at all, but the basic point is if the expanding horospherical subgroup is contained in P, then this P-invariant measure is actually invariant not under P, but under the centralizer of this element A. This is a standard technique. I mean, it's, yeah, used in, yeah, proof of the Margulis superrigidity theorem and things like that, use arguments like this. We show that P is actually invariant under the centralizer of an element. Okay, and now I'm not going to prove this key fact, but let me show how it implies the hard part. This is, once you have this, the hard part's easy to prove. The point is that let's take a to the n. We can pick any element A we want, as long as u comes out to be right. So let's take a to the n. Let's take a to be at two big things that are equal, and then a small thing. So these two are equal. Then what gets expanded is exactly these things in the right-hand column. It's not hard to see that if you conjugate by something that looks like this, it's these entries that are going to get bigger. That's definitely contained in P. So it's invariant under the centralizer, and the centralizer of something here, remember these two big entries are equal, will exactly be this upper left corner thing. And on the other hand, we can let A to n be opposite, take one big thing and two small things. Then instead of the expanding horosphericals being a column, there'll be a row. So that again is contained in P. So mu P is invariant under the centralizer, which is this bottom part here. Well, these centralizers generate all of G. So what that means is that, well, mu P is invariant under both of these. So it's invariant under the subgroup where they generate. Mu P is actually invariant under all of G. And in particular, it's invariant under K. So when you translate mu P by K, this actually is just mu P. We're integrating mu hat is the integral of mu P. Well, if you integrate a bunch of copies of mu P, you're just going to get mu P. So so mu hat is equal to mu P, but mu P is G invariant, and that's what we're trying to prove. We showed that it was equal to a G invariant measure, so it is G invariant. And I should say, this argument definitely uses higher rank. In real rank 1, the centralizer of an element is just going to be A again. It's not going to give us any bigger. We're not going to be able to get anywhere by applying this key fact. So we definitely need a higher rank in order to prove the theorem. And this is another key place where higher rank is used. And yeah, that's all I had to say. So thank you very much.
Is there any other rank 1 lattices which is left-orderable?
That's a very good question. The question was whether there are any other rank 1 lattices. I mean, I said that SL2Z is left-orderable. That's trivial because it's a free group, or finite index. Yeah, the question was whether there are other rank 1 lattices that are left-orderable. It's very much open. There are examples that are known. And in fact, the only examples I can think of, there's got to be something else. But yeah, so SL2Z is a lattice in SO12. Well, it turns out also, if you take any lattice in SO13, it was proved by Ian Agol a few years ago that it will actually be left-orderable. Sorry, a finite index subgroup will be left-orderable. So there are many, many lattices in SO13 that are left-orderable. And I think there are some other examples known in some larger SO1Ns, but I can't swear to that. But in SU1N, in the other rank 1 groups, it's not known. We don't have an example that is. It's easy to find examples that aren't, but we don't know any examples that are. And I guess, yeah, we don't, yeah, it's very much open. So it isn't just SL2Z, but if you get past SO13, then it's going to be very rare. But actually, maybe, I don't know, maybe Venki knows something about this, but yeah, I don't know rank 1. But yeah, there are some examples, but it's very limited. Our knowledge is limited.
And it is not so in the case of the hyperbolic 3 manifold, is it not only for arithmetic?
Right. So arithmetic, I guess that's the kind of thing that had been known by, yeah. So for the arithmetic ones that had been known for a long time, 20 years maybe, 30 years, I'm not sure. But then it's the non-arithmetic ones. It was shown by Ian. Yeah, the point is that as soon as this is special to SO13, as soon as you know that the lattice has a homomorphism onto Z, as soon as you know that the abelianization is infinite, and if it's also torsion free, then it's going to be left orderable. I think I've got that right. But anyhow, that's the key thing.
I see. So I see. So it's a corollary of the virtual fibering or something like that.
Yeah, exactly. It follows from, it had been known that if you could prove that, so the point is that, it was all set up. As soon as Ian Agol proved his theorem, this was automatic because it had been known that was what you needed.
Okay, thank you very much.
Yeah.
Question? Remark? Thank Dave again. Thank you very much.
Okay, thank you.
Thanks, Dave. See you later. Thank you.